In chapter 6.2, we discussed orthogonal set. So we start with the definition of the orthogonal set. A set of the vectors is said to be an orthogonal set if a pair of distinct vectors from the set is orthogonal. For example, uj in a product ui in a product uj is equal to 0 whenever I is not equal to j. So set A is an orthogonal set of the non-zero vectors, then S is a linearly independent, hence is the basis for the surface spanned by S. So we prove this one, and similarly, we define a definition orthogonal basis for the subspace W of the Rn space is the basis for the W that is also orthogonal set. And if Y in subspace W, if the set of the vector U be an orthogonal basis, then Y can be represented by looks like this: linear combination of the vector U with the coefficient Ci or Cj defined like this. We also prove this one. Yeah, and we also discussed the orthogonal projection concept. Y can be decomposed as the Y hat plus Z. Z is equal to Y minus Y hat. So here we called Y hat is called the orthogonal projection of the Y onto U, where vector Z is called the complement of the Y orthogonal to U. And what's that? Yeah. Sometimes Y hat is denoted by projection L of the Y, which is called the orthogonal projection of the Y onto L. What else? Yeah. Yeah. We also discussed orthonormal set. Orthonormal set is similar to the orthogonal set. The main difference is the length of the vector in orthonormal set should be 1. So it should be univector. Looks like this. Yeah, it was the examples of the orthonormal basis because the length of this vector, each vector was 1, and inner product between each other was 0. So V1, V2, V3 is an orthonormal set. Also normal set or orthogonal set. 그렇죠? Like this. Yeah. So today we will finish the lecture note 8 here. This is theorem 6 on n by n matrix U has orthonormal columns. So for example, the U consisting of the vector U1, U2, and UN, not n, small n, and each vector U in or M space. Matrix n by n matrix has also normal column. I mean the U vector U's also normals if and only if U transpose U is equal to identity matrix. U transpose U is equal to identity matrix. So this is theorem 6. Okay. So first of all, what is the size of the matrix I here? So what is the size of this one? I. If matrix U is m by n. In this case, I is in n by n, right? n by n. 그렇죠? n by n? No. n by n. Why? Because U transpose is in n by m and U was n by n. So it should be n by n. 그렇죠? Thank you. Right? So let's prove this one. It's very, very simple. We suppose that you have only 3 columns, each a vector in R3 space, then U can be represented by U1, U2, U3. And let's compute U transpose U. U transpose was like here, U is here. 그렇죠? Because U is here, U transpose is going to look like this. Then let's compute this matrix multiplication. So first term, this term should be this vector times this vector, 그렇죠? Because this one in each vector in R3, so should be 1 by 3. Then this one is in 3 by 1, so it should be this one. It's going to be scalar value. And this one, it's going to be this vector times this vector. This one, it's going to be this vector times this vector. Blah, blah, blah. We can finally achieve this matrix. To make this matrix as an identity matrix, the diagonal term should be 1, and off diagonal term should be 0. Here, should be 0. From this observation, columns of matrix U also gonna if and only if this one, and this one and this one is 0, this one is 0, this one and this one is 0. So off diagonal term here, and here. 그쵸? Columns of matrix U all have a unique length if and only this one, and this one. Satisfy. Let's suppose that this is a matrix 3, and this is matrix 4, and this is equation 5. This theorem follow immediately from the 3 to 5. So if U transpose U is equal to identity matrix U, M by M matrix U has also normal column. This is theorem 6. It's very intuitive. And one more theorem is let matrix U be an M by M matrix with also normal column. So maybe from the previous theorem, U transpose U is equal to identity matrix. And let X and Y be in Rn space. Then 3 properties should be satisfied. First of all, length of the UX is equal to length of the X, and UX inner product to UY, it's going to be the X inner product to U, X inner product to Y, and UX inner product to UY is equal to, should be 0 if and only if the X inner product to Y is equal to 0. So let's prove this one. Let's prove the A. So first of all, length of the UX is going to be the square root of the UX transpose UX, right? So from the definition of the transpose of the matrix, it's going to be X transpose U transpose U X transpose, right? Because the matrix U is also normal, U transpose U is equal to 0, I. So it's going to be I. Then this one is going to be square root of the X transpose X. It's going to be the length of the X. It's very simple. Right? Similarly, you can prove P and C very easily. For example, Y. For example, from here, from the definition of the inner product, UX transpose UY should be X transpose UY, because the U transpose U was identity, so it's going to be X transpose Y. Right hand side. 그렇죠? Similarly, you can prove the statement C. This is theorem 7. In fact, the properties of A and C say that the linear mapping X to the UX preserve the length and orthogonality. So what does it mean? So if, okay, let's go back to our matrix equation, A equals B. If our matrix A substituted by matrix U, in this case, also normal matrix, let's suppose that X is defined here, and arbitrary matrix U transform matrix vector X to the UX, right? And let's suppose that there's another vector Y, and it is transformed to the UY. Then statement is A and C shows that length of the vector length of the vector x should be preserved in length of the ux, vector ux, and orthogonality between x and y should be preserved in ux between ux and uy. So what does it mean? If we think in 3D space, let's suppose that vector x is here, vector y is here, and let's suppose that they are orthogonal each other. Then transform the matrix, transform the vector ux and uy. The length of the length of the x and length of the ux should be same. And orthogonality should be preserved after transformed by matrix U. This is the properties of orthogonal matrix. We'll use this kind of concept in QWERTY composition. So here, please just remember what I explained. Okay. So this is the end of the chapter 6.2. Question. 자, 여러분 어렵지 않죠? 그래서 저번 주부터 우리 해온 거는 이제 orthonormal set 그리고 orthonormal matrix와 같은 어떤 컨셉추얼한 얘기들만 계속 해오고 있어요, 그렇죠? 이제 이러한 컨셉추얼 얘기를 이제 오늘 강의까지 듣고 이제 6.4절로 넘어가면 이제 QRT composition 또는 어떤 linear square solution과 같은 어떤 우리가 systemical way to solve your linear system 우리 이제 derive 하기 위해서 이런 컨셉들을 지금 배워가고 있는 거예요. 조금 어렵겠지만 이제 이게 이제 무슨 의미를 가지는지만 여기서 좀 이해를 했으면 좋겠어요. 알겠죠? 자, 질문. No? Okay. Then let's move to the lecture note 9. Orthogonal projection. Orthogonal projection. This is just extension of the chapter 6.2. So this is about 6.3, chapter 6.3, called orthogonal projection. Okay, let me start. So in previous chapter, we discussed the orthogonal projection of the point in R2 space onto a line through the origin. So in previous chapter, we discussed how to understand orthogonal projection of y onto the line, let's suppose L, spanned by arbitrary vector u, where u is defined looks like this. And we discussed the orthogonal projection y hat, right? And orthogonal vectors w, something like this, right? And we discussed y can be decomposed as a y hat plus w. Then in this chapter, we will extend this concept to the arbitrary Rn space, not a R2 space anymore, general Rn space. Then it has important analogy in Rn space. Okay, let's get started. So here's the general definition of the orthogonal projection in Rn space. Given a vector y, and subspace W in Rn space, let's suppose that we have some arbitrary subspace W here and arbitrary vectors y here. And in this case, there is a vector y hat in subspace W, such that y hat is the unique vector in W for which y minus y hat is orthogonal to W. So here exists y hat if y minus y hat vector y minus y hat orthogonal to W. So this vector should be orthogonal to the subset W. And y hat is unique vector in W closest to y. Closest to y. Y hat is the unique vector. unique vector, 그쵸? 무조건 하나 있다는 거예요. unique vector in W closest to y. y라고 하는 거와 이 subspace 안에 있는 요 subspace 안에 있는 벡터 줄 중에 가장 가까운 벡터가 이 y hat이다 라고 하는 거죠. closest to y. 가장 가까운 y hat이라는 거다. So this is the basic concept of the orthogonal projection. So in this case, this one is called orthogonal projection of y. Onto subspace W. This is just the extension of previous concept to the Rn space. 그렇죠? These two properties of the y hat. 그렇죠? First properties and second property. 그렇죠? Second properties. These two properties of the y hat provide a key to finding the least square solution of a linear system, which will be told in the chapter 6.5. So what does it mean? Why do we have to discuss orthogonal projection from the last week to this week? Why? So let's go back to our AX equals B. Let's suppose that we have a linear system AX equals B. A is in n by n space, X in n by 1 space, then B is in n by 1 space. Now let's draw this relationship here. AX is going to be the linear transformation Rn to Rm space, Rm to Rn space, X to the AX. Then it should be right. So from here. So first of all, what is column space of matrix A in this figure, in this illustration? What is a column space? How we can draw column space in this figure? 자, 요렇게 우리가 이제 그릴 수 있죠. AX 플러스 B가. 자, 컬럼 스페이스 어떻게 그려주죠? So, first of all, what is the definition of the column space? What is that? 자, 여러분 다 잊어버렸지 않았죠? 자, what's column space? Linear combination of the column vector A, right? And column space should be the span of the columns of matrix A. 그렇죠? right? Right. So maybe it should be here. 그렇죠? Column space matrix A. Let's say this is arbitrary subspace W, column space. So what happens in column space? In subspace W, I mean the column space, every vector in column space, let's say P, should have the corresponding vector X. So I mean within the column space, every matrix equation AX equals B should have solution. I mean, for the vector B in column space, X equals B should have always solution. This system consists. But in many cases, I mean, as you know, Rn space. Let's think about Rn space. Rm space. Rm space is continuous and infinite space. 그렇죠? Infinite space. It's really huge space. So in other words, most of vector in Rn space, not in column space. Maybe here. Most of vector C, arbitrary vector C, is not in column space. It means that most of the equation Ax is equal to C does not have solution. Does not have any corresponding vector X in Rn space. So in this case, we call Ax equals C is inconsistent. So as we discussed previously, most of your linear system, in practice, most of your linear system, this looks like this. Most of your linear system will be inconsistent system. So you may not solve your linear system with the technique we discussed so far. So what happened? So what should we do next? Because we can't solve inconsistent system, maybe you can just say, so this is inconsistent system, so we can solve the solution. So we can't find a solution for this linear system. But we want to do better. We want to generate, we want to find, let's use the different color. We want to find approximate solution. Even though we can't find the exact solution of Ax equals C. Our objective is to find the approximate solution of this case. Then this is the least scale solution of the linear system. The question is, what is the approximate solution of the Ax equals C in case that Ax equals C does not have the exact solution? That's the point of this remaining chapter. That's the point of this remaining part in this semester. To conclude, we want to find out nearest point here. We want to find out nearest point, let's say C hat in W space, because in this case, C hat maybe have the corresponding solution that we want to say this is our approximate solution. We want to say this one. This is our approximate solution. So how can we find out this one? Closest point. Closest point of vector C onto W space. This one. Orthogonal operation of the Y onto W. So this vector is going to be the orthogonal operation of the C onto column space of matrix A. In other words, if we can find out this one, orthogonal operation of the Y onto W space, then we can find out this vector, then we can finally find out approximate solution for this inconsistent system. That's the topic of the least scale solution, and this is the topic of the remaining part of in this semester. 그렇죠? 그래서 한 번만 설명할 게 너무너무 중요한 파트니까, 자, 우리가 지금까지 저번 주부터 왜 이렇게 orthogonal 프랙션에 대해서 얘기를 해왔느냐를 이제 설명해주는 그림이에요. 자, 우리 이제 배웠던 거 쭉 얘기해 봅시다. 우리는 요걸 얘기해왔어요. X equals P. 그렇죠? X equals P 어떻게 그래요? 어떤 Rn 스페이스에 존재하는 X를 Rn 스페이스로 트랜스폼하는 어떤 매트릭스 A가 있을 때 이 B가 정해졌을 때 X를 찾는 문제였죠. 근데 B가 솔루션을 가지는 X들의 조합, 우리가 컬럼 스페이스였어요. 그렇죠? 근데 말했지만 대부분의 여러분들이 가지고 있는 매트릭스 C, 벡터 C는 이 컬럼 스페이스상에 존재하지 않아요. 즉 무슨 얘기냐? Your linear system X equals C는 대부분이 inconsistent 시스템일 거예요. in practice. 그렇죠? 실제로 많은 상황들에서 그리고 매트릭스의 사이즈들이 커지면 커질수록 대부분의 이그젝트 솔루션들이 존재하지 않는 경우가 대부분이에요. 그런 경우에 자, 여러분들 시스템 솔루션이 존재하지 않는다라고 끝이 아니라 우리는 approximate 솔루션 이 시스템의 완벽한 솔루션은 모르지만 approximation 된 즉 근사한 솔루션 즉 이 inconsistent 시스템을 가장 그래도 잘 표현할 수 있는 매트릭스 벡터 X를 찾고 싶은 게 approximate 솔루션 찾고 싶은 게 우리의 목표고 이게 바로 리스크 계열 솔루션이에요. 이게 이제 챕터 6.5에서 얘기할 건데 그게 뭐냐? 이 C와 이 서브스페이스 W 컬럼 스페이스와 가장 가까운 점을 찾아서 진짜 거리로 가장 가까운 점을 찾아서 그때의 솔루션을 찾으면 그게 AX 코치를 표현하는 가장 가까운 솔루션이다 라고 하는 게 우리의 목표인 거죠. 그쵸? 그쵸? 왜냐? 이게 할 수 있는 우리의 최선이기 때문에. 왜냐? 우리는 AX 코치 B 즉 솔루션이 존재하는 경우에만 솔루션을 찾을 수 있기 때문인 거죠. 그쵸? 이 얘기를 하기 위해서 결국에 뭐냐? 어떤 벡터 C에서 어떤 서브스페이스 W로 가장 가까운 포인트가 뭐냐? C hat closest point가 뭐냐는 질문을 답을 해야 되고 그게 이제 바로 이제 저번 주부터 오늘 얘기할 also operation of the y onto w 즉 유니크하면서 가장 가까운 포인트였던 y hat을 어떻게 찾을 건가 라고 하는 문제로 귀결을 하는 거죠. 이해됐죠? question. 자, 여러분 너무너무 중요하니까 지금 혹시 이해가 안 되면 알려주고 이걸 지금 모르면 아마 여러분 리스큐어까지도 무슨 소리인지 하나도 모를 거예요. 자, 혹시 방금 제가 한국말로 한번 설명드렸는데 If there are any question, please let me know now. 그렇죠? 자, 한번 혹시 이해가 안 되면은 한번 질문 한번 우리 해봅시다. 여기까지. 요걸 이해해야 여러분들이 더 나갈 수 있어요. 알겠죠? question. Are you clear so far? 자, 여러분 여기까지 완벽하게 지금 이해했나요? 네, 질문 있으면 다 질문해주고 이해했으면 혹시 이해했다고 좀 알려줘요. 자, 서현 학생 질문이 리스크 솔루션 분야에 있었던 것 같아요. 보면 AX가 반드시 컬럼에 속하도록 하고 B가 가장 벡터를 찾는 벡터. 자, 리스크 솔루션 맞아요. 그러니까 그쵸. AX가 컬럼 A에 속하면서 그게 벡터 C와 가장 가까운 벡터를 찾는 거고요. 그때 그 벡터에 그쵸? 그거를 B hat이라고 했을 때 AX equals B hat의 솔루션이 리스큐어 솔루션이다 라고 이해하면 될 거예요. 그쵸? 결국에 어쨌든 솔루션은 X 요 스페이스상 정의가 되어야 되니까 알겠죠? 오늘 어차피 리스큐어 솔루션 할 때 완벽하게 설명을 해줄게요. 근데 이제 오늘 배울 얘기들은 요걸 배우기 위해서 요 클로즈 포인트를 찾아가는 과정이다 라고 이해해 주시면 돼요. 알겠죠? Other student? 자, 누가 있었지? 예담? 학생. 매일 질문하는 친구. 또 누구 있었더라? 형민 학생. 아니 또는 다른 학생들. 자, 다 이해했나요? No more question? Good. Nope? Okay. Now let's move. So, then here we will just extend the concept defined in the R2 space here to the Rn space. 그렇죠? Rn space. So, if a vector Z is orthogonal to the every vector C in subspace W of Rn space, then Z is said to be the orthogonal to W. Looks like this. Let's say subspace W is here, vector Y is here, then vector Z is orthogonal to every vector in W. Then we say that Z is orthogonal to W, subspace W. Then the set of the all vector Z that are orthogonal to W. Orthogonal to W is called orthogonal complement of W is said to be W. 이거는 뭐라고인지 모르겠네요. W like this. 그렇죠? orthogonal complement of W. A vector X in W, orthogonal complement of W, if and only if X is orthogonal to every vectors in the set of the set that span W, and the orthogonal complement of the W is subspace of Rn space. So there exists arbitrary subspace looks like this. This can be represented by looks like this. So this is called set of the order vector Z is called the orthogonal complement of the W. And then let's derive orthogonal decomposition theorem. Orthogonal decomposition theorem. This is theorem A. This is theorem A. Let W be a subspace of Rn space. Then each Y in Rn space can be written uniquely in the form Y is equal to Y hat plus Z, where Y hat is in W, Z is in orthogonal complement of the W. And it should looks like this. W space is here and Y. Vector Y should be here, and if 0 is here, then Y hat should be uniquely determined, and with vector Z, Y can be represented by sum of Y hat plus Z. In fact, if Y1, Y2, Yp is any orthogonal basis of the W, any orthogonal basis W, then Y hat, orthogonal operation, Y hat can be represented by Y hat equals blah 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 times U1 blah blah times UP, and Z, orthogonal complement matrix vector Z is equal to Y minus Y hat from here. So to understand this, we can just derive this equation. Then we have the way to find the orthogonal operation of the Y hat by only using vector Y1, Y2, and Yp with the U1, U2, and Up with the matrix vector Y from here. So this is called orthogonal decomposition theorem. This is the way to find out Y hat and Z given Y and W. Y and W. This is orthogonal decomposition theorem. In other words, before proving this one, vector Y hat here, Y hat is called orthogonal projection of the Y onto W. Orthogonal projection of Y onto W often is written as projection of Y onto W. Project W Y. Project W Y. Looks like this. This is the subspace W, and this is vector Y. Then Y hat should be projection of the Y onto W. Then orthogonal complement of the Y should be Y minus Y hat. And then these two vectors should be orthogonal each other. This is the definition of the orthogonal operation Y onto W, this one. So this is a way to compute the orthogonal operation Y onto subspace W. This is also orthogonal decomposition theorem. So, first of all, let's prove this one. It's very, very easy, and it's very, very similar to the theorem in the chapter 6.2. Let's do that. So first of all, let U1, U2, UP be any orthogonal basis for W, arbitrary orthogonal basis for W. Let's define y hat by 2. So in this case, it was the equation 2, and it was the equation 1 in your textbook. Yeah. Let this one is any orthogonal basis for W, and let's define y hat by 2. Then y hat is in W because y hat is a linear combination of bases. This one, linear combination of bases. This is the linear combination of UP. 그렇죠? So y hat in double space. 그렇죠? Then let's Z is equal to y minus y hat. Since U1 is orthogonal to U2, U3, UP from the definition, because they are coming from the orthogonal basis. 그렇죠? Then it follows from the here. 그렇죠? Second equation. Z in the product U1. Z product U1. It's going to be the Z, because Z is equal to y minus y hat. So y minus y hat times U1. Let's find that U1. Then y in the product U1 minus, because y hat defined looks like this, by substitute this one to here, this equation looks like this. So this zero vector coming from the y2 in the product y1, because they also normally zero, so the remaining term is going to be zero from this one. 그렇죠? And then from the second term, this one is going to be 1. These two terms can be eliminated. Then y inner product u1 minus y inner product u1, then it's going to be 0. So in other words, vector z is orthogonal to u1. Vector z is orthogonal to u1. Similarly, z is orthogonal to each uj in the basis for w. Z is orthogonal to u2, Z is orthogonal to u3, or Z is orthogonal to up, something like this. Hence, vector Z is orthogonal to every vector in W. 그렇죠? Then Z is in orthogonal complement of matrix subspace W. 그렇죠? From here, every vector mean C1, because the vector U were a basis for the subspace W, so every vector something like this should be orthogonal to the matrix vector Z due to this fact. 그렇지? And to show that decomposition in 1 is unique, decomposition 1 here, 그렇죠? Decomposition 1 is unique. Suppose y can also be written as y minus y 1 hat plus z1. With y1 hat is in W, z1 hat is the orthogonal complement of W. Let's suppose there are another vector y1 hat, z1 hat, z1. Then y hat plus z should be equals to y1 hat plus z1, since both sides equals to y. So y hat minus y1 hat is equal to z2 minus z. This equality shows that the vector v is equal to y hat minus y1 hat is in W and in W hat space, because the Z1 minus Z2 are both in orthogonal complement of W, and orthogonal complement of W is the subspace each other. Then V inner product of V is equal to 0, which is show that V is equal to 0. It proves that y hat is equal to y1 hat. Also Z1 is equal to Z. So in other words, decomposition with y hat and Z should be unique. That's it. This is proof of this one. This orthogonal decomposition theorem. So, in other words, vector y can be written uniquely in the form of y hat plus z, where y hat is in the subspace W and z is in orthogonal complement of subspace W, and any orthogonal basis of the W, y hat can be represented by looks like this. This equation. This is orthogonal decomposition theorem. It was proved by here. 그렇죠? 이렇게 증명할 수 있다. 하는 거죠. 자, 한국말 더 설명할게요. 자, orthogonal decomposition theorem. 자, 증명은 어려웠죠. 여러분 하면 되겠지만 증명이 중요한 게 아니에요. 그렇죠? 이해를 해야 돼요. 자, 어떤 subspace W가 있고 어떤 Y가 있을 때 그 subspace 밖에 있을 수도 있고 안에 있을 수도 있어요. 어떤 밖에 있다고 쳤을 때 뭐 안에 있어도 상관없어요. 근데 일단 밖에 있다고 쳤으면 y 플러스 z로 표현될 수 있네요. y hat은 어떤 w 안에 있고 z는 w의 orthogonal 벡터로 표현될 수 있는데, 이때 y hat은 유니크하다. 그리고 그때 y hat은 이 orthogonal 베이시스들로 이런 식으로 표현될 수 있다 라고 하는 게 orthogonal decomposition theorem이라고 하는 거예요. 알겠죠? 어렵지 않죠? Question. So first of all, let me show you examples for the that can benefit from the orthogonal decomposition theorem. So let's suppose that we have a matrix vector u1, u2, and y. u1, u2, and y. And first of all, observe that set u1, u2 is also orthogonal basis for the w spanned by u1 and u2. We already know this one, right? So let's suppose that here is the subspace W, which is spanned by u1 and u2. u1 and u2. This is subspace W. Then let's write the y. Let's suppose that y is here, maybe outside the subspace. Then let's write the y as a sum of the vectors in W and vector orthogonal to W. So the question was, what is the orthogonal complement of y onto W, and what is orthogonal projection of the y onto W, and what is orthogonal complement to W. This is the question of finding y hat, and vector orthogonal W is called the Z. Then here the summation. So y is equal to y hat plus z. The question is, what is y hat and what is the z in this case? This is our question. So because we already have the equation here, then we can just solve this equation. So first of all, orthogonal projection of the y onto W is y hat is equal to y in the product u1 over u1 in the product u1 times u1 plus y in the product u2 over u2 in the product u2 times u2 by definition of the orthogonal theorem. Because we already know y, u1 and u2, let's solve this one. So first of all, from here, vector y in a product u1, it's going to be the 1, 2, 3 times 2, 5, negative 1 over 2, 5, negative 1 times 2, 5, negative 1. So from here, it's going to be the 2, 10, 2 plus 10 minus 3. It's going to be 9 in this case. And it's going to be 4, 25 plus 1. It's going to be 30. So you fill 9 over 30 with vector u1. Similarly, you can compute this one. It's going to be the 3 over 6 with u2 here. Then this equation, it's going to be a negative 2.2 over 5 to 1 over 2. So that y hat, it's going to be looks like this. So it's very, very simple. And y minus y hat, which is vector z, it's going to be y was 1, 2, 3, y hat was looks like this. Then z, it's going to be the 7 over 5, 0, 13 over 5. 13 over 5. The orthogonal decomposition theorem ensures that y minus y hat is in also complement of the substrate W. To check the calculation, verify the y minus y hat is also going to both u1 and u send hands toward the W. So you can easily compute this question is correct. So by compute this one is equal to 0. So desired decomposition of the y, it's going to be the y is equal to y hat. Y hat and z is here. Y hat z is here. In other words, in this case, y hat was negative 2 over 5 to 1 over 5, and z is equal to 7 over 5, 0, 14 over 5, 14 over 5, 14 over 5. This is the orthogonal decomposition of the matrix or arbitrary matrix Y onto subspace W. So, in other words, this vector y hat is unique and closest to y in space W. That's also operation. That's also operation. 자, 알겠죠? 여러분, 자, 결국에 우리가 뭐야? 아까 그 올소나 티어럼, 올소나 디컴포즈 티어럼 측만 알면은 우리가 어떤 arbitrary matrix, arbitrary vector y가 있었고 어떤 subspace w가 있었을 때, 그렇죠? The closest point는 뭐예요? 이 subspace의 orthogonal basis. 여기선 u1, u2죠? orthogonal basis를 찾아서 그냥 orthogonal basis를 가지고 그냥 요식을 풀면은 y 햇이 나오고 z는 너무 쉽게 y-y 햇을 그냥 구해버리면 되니까 이렇게 z와 y 햇을 쉽게 구할 수 있다라고 하는 게 orthogonal decomposition theorem이에요. 이거 왜 알아야 되느냐? 아까 말한 요거 알려고. 그렇죠? 지금 요 작업들 하고 있는 거죠. 그렇죠? 요거 알기 위해서. 그렇죠? 요거 하려고 하는 거죠. 요거. 조금 렉이 있네요, 지금. 네. 요거 하려고 하는 거죠. closest point. 그렇죠? To find out approximate solution of your inconsistent system. 그렇죠? This is also an operation. 알겠죠? Question. Maybe a little bit challenging to understand what I mean, but it's really easy to compute, right? It's really easy to find out also fraction y hat because this is just a simple calculation. 그렇죠? This is very, very easy calculation. Question. 자, 여러분 우리 조금 질문 좀 받고 갑시다. 여러분들이 어디까지 따라오고 있는지 제가 잘 모르겠는데 자, 잘 따라오고 있나요? 어때요? 좀 빨라요? 아니면 혹시 뭐 이해가 안 되는 부분이 있으면 한번 알려줄래요? 잘 따라오고 있나요, 여러분? So, by the way, we had the homework 5, which we'll cover from the chapter 6.1 to the 6.2, maybe? No? It covers chapter 2.9 to chapter 6.1 and 6.2. 그렇죠? 우리 숙제 있는 거 잊지 말고. Question so far. 자, 그럼 혹시 잘 따라오고 있어요? 아니면 혹시 이해가 안 되나요? 아니면 벌써 포기했나요? 어때요? 듣고 있는 친구들 의견 좀 줄래요? 아무도 안 듣고 있나요? 자, 괜찮아요? 다 이해했어요? 오케이, 오케이. 좋습니다. 네. 다 이해했죠? 자, 모르겠으면 지금 물어봐야 돼요, 여러분. 알았죠? 왜냐면 이제 우리 이번 학기 사실 해봤자 얼마 안 남았어요. 그쵸? 많아야 한 달. 그쵸? 여러분들이 아마 우리 볼 수 있는 시간이 많아야 한 달인데 지금부터 이제 나오는 컨셉들은 지금 오늘 나온 얘기들을 계속 확장을 할 거기 때문에 이걸 이해 못하면 아마 계속 모를 거예요. 말했지만 뭐 다른 과목들도 뭐 마찬가지겠지만 사용돼서 모르면 이번 학기 모르면 끝이 아니고 여러분은 아마 지금 특히 2학번 애들 졸업할 때까지 모를 거예요. 많은 과목들에서 이해해야 돼. 알았죠? 자, 이해했죠? 혹시 모르는 친구 질문 해주고. 잠깐만. 근데 여러분 지금 혹시 지금 축제 기간이에요? 2학번 친구들 혹시 이번 주예요? 다음 주인가? 축제 하고 있어요? 다음 주? 그래. 다음 주는 생각해 봅시다. 다음 주? 그래 여러분 축제하느라고 지금 수업을 안 듣는 줄 알았어. 그러니까 축제 전이니까 열심히 들읍시다. 알겠죠? 네. 자, 가봅시다. 우리 여기까지만 끝낼게요 오늘. So today we will finish with one more concept. Geometry interpretation of orthogonal projection. Let's understand orthogonal projection in a geometric view. So let's suppose that we have a matrix. We have a vector y. 그쵸? We have a vector y here, and we have a vector u, and u1 and u2, something like this. Then, what is the meaning of the orthogonal projection? So, in other words, let's suppose that we have a substrate W spanned by U1 and U2. Then, what's the geometric meaning of this orthogonal projection Y hat? This orthogonal projection Y is the sum of its projection onto one-dimensional subspace that are mutually orthogonal. What does it mean? So it means that let's suppose that U1 and U2 is orthogonal each other. Then let's suppose that vector Y can be projected to this line. 그쵸? This line spanned by vector U1. Similarly, this vector Y can be projected to this line spanned by U2. Spanned by U2. So then, in this case, from the chapter 2.1, this point, y1 hat, y1 hat, it's going to be this one. y inner product u1, u1 inner product u1, u1. 그렇죠? Really? Let's go back. From here. 그렇죠? This one. This one. 여기서부터 그렇죠? y랑 u랑 이너 프로덕트 한 다음에 u 이너 프로덕트 u로 분모하고 u 곱하는 거. 그렇죠? 되죠? Similarly, this one. y2 hat. It's going to be defined also like this. Then y hat. It's going to be a sum of these two vectors. These two vectors. Then y hat. It's going to be sum of this one. y1 hat plus y2 hat. So by Orson operation theorem, y hat can be formulated this way. Looks like this. Formulate looks like this. This is the definition of the y hat. This is the definition of the y hat. One more thing is that y1, y2, yp is an orthogonal basis for the w, also base w, and if y happens to be in w, it means that w is here. If y is in this space, y happens to be in w space, then the formula for the projection of the y onto w is exactly the same as the representation of y given the theorem in chapter 6.2. It means that y hat or projection of y onto w, it's going to be exactly the same to y. Exactly the same to y. In this case, if y is in w spanned by u1 and u2 and up, then projection of the y onto w is equal to y. That's it. Again, if y is in w spanned by u1, u2, and up, where u1, u2, and up are orthogonal basis for the w, then orthogonal projection of y onto w is equal to y itself. It should be same. Then y is going to be the projection of the y onto w is going to y itself. 그렇죠? This is the properties of the orthogonal projection. 그렇죠? Question. No? Right, so that's it. So this is the properties of orthogonal operation. Third day we will move to the path approximation theorem, and next week we will move to the what's that? Gram-Schmidt process and dual decomposition. Okay. Other question? No. So before the finish, please remember we have a homework 5 which is due on this Thursday. So please try to solve yourself, and yeah, that's it. No more question. Okay, so that's it. So this is the end of today's lecture. Thank you very much and see you next week. 자, 여러분 오늘 고생 많으셨고요. 우리는 또 목요일 날 보도록 합시다. 수고하셨습니다.